Hey folks, wanted to do a quick practice problem with you guys and give you guys a couple of different practice problems so you can see some of the wording on this, and also wanted to provide a little bit more information about the notes from the other day and kind of what the equation is going to look like that we're going to be living off of, which is basically Einstein's equation. Okay, so we're focusing on the photoelectric effect, and I've got two different diagrams here, and they're both exactly the same, but notice this one has the kinetic energy of the photoelectrons in joules. This one has the kinetic energy of the photoelectrons in electron volts. Okay, so two different units, both energy units. Okay, so remember, Einstein figured out that the photoelectric effect basically provided evidence for Planck's quantum theory of light, basically thinking of light as photons, which is just individual packets of energy rather than waves. And Planck's equation is E equals hf. Okay, so basically what Einstein figured out is, so remember, for a photoelectric surface, so imagine we have a metal, and you'll get to see this in another day or two, so just bear with me on this. Imagine you have a metal surface and you have light coming in and it's going to strike the metal, okay? So all of the energy that is incident is coming from the photon. So your initial energy is from the photon. Okay, now some of that energy, though, is going into removing the electron from the atom. So let's say we have sodium or potassium metal, and light is incident upon it, and we get the electron to be removed from the surface of the metal. Okay, this is called the work function. So part of this energy of the photon just goes into removing the electron from the atom. Okay, so this is the symbol for the work function that I'll be using. I know in the notes it was a W naught, but this is the one that I use. Okay, now any excess energy beyond that, so let's say the photon has more energy than what's needed just to remove the electron, the rest of the energy goes into the kinetic energy. Okay, so if we look at kinetic energy, oh, I forgot to label my x-axis, so I'll take a point off myself later. This is frequency on the x-axis. If we graph out kinetic energy of the photoelectrons versus frequency, the slope of the line is going to be Planck's constant. Okay, now if we write a straight line equation for this, we have our y equals mx plus b, and this will actually be minus b because this is going to be a negative y-intercept down here. If we take this equation and we rearrange it a little bit, and we put kinetic energy maximum on the y-axis, and the m value is Planck's constant, and x is frequency, we will see that h times f, which is the energy of our photon coming in, and then this is minus the work function, okay? Now, the equation for the work function is exactly the same as hf, because remember, if this energy of the photon is just enough to get this off, then this is also equal to h times f down here. But notice I changed the symbol. I put f naught. This is what's called the cutoff frequency, okay? So the work function is equal to Planck's constant times the cutoff frequency. So the cutoff frequency, basically, remember, if we would put red light onto the metal, nothing was ejected because that wavelength was too long or too low of a frequency, and it did not reach the cutoff frequency, or it was less than the cutoff frequency, so no light was, or no electrons were ejected. Okay, so next. There are two values for H we can use, and it really depends on if we want to use it in joules or electron volts. Okay, electron volts are sometimes a little bit easier to deal with because the numbers are a little larger. We're not talking about very large energies here. I mean, we're talking about very, very tiny amounts of energy. So the numbers will get very, very small. Planck's constant is 6.63 to the negative 34th joules seconds. Or if we convert this to electron volt seconds instead, and we divide this by 1.6 to the negative 19th, we end up with 4.14 to the negative 15th electron volt seconds, okay? So if the kinetic energy is in electron volts, the slope of the line is 4.14 to the negative 15th. If the kinetic energy is in joules, the slope of the line is 6.63 to the negative 34th, okay? All right, let's move on to a couple of practice problems. And I have no idea why my camera took one page as yellow and then the other page like this, but that's okay. All right, so a photoelectric surface has a work function of 3.7 to the negative 19th joules. We want the minimum frequency needed to eject the electrons. Okay, so basically what we're looking for in this problem is the cutoff frequency. So since the kinetic energy will be 0, that means that HF is equal to the work function. And if we plug 6.63 to the negative 34th times the frequency, we will get 5.6 to the 14th hertz. So that's a pretty easy question. There's not a whole lot to that. We just have to understand that the work function is equal to H times F, but it is the cutoff frequency. All right, now let's exceed the cutoff frequency. Let's say we put 400 nanometer violet light and we have that incident upon potassium that has a work function of 2 electron volts. And we want the maximum velocity of the photoelectrons. Okay, so if we use Einstein's equation, K equals HF minus the work function, and this is usually the way I started. I know we can write it as a conservation of energy statement and say HF equals K plus the work function, but this is the way this equation is usually written. Now, since this is in electron volts, notice that I used the 4.14 number, okay, but 400 nanometers, you can convert it to the frequency if you want, or we know that the wavelength or frequency equals C over the wavelength. So notice I took 3 times 10 to the 8th divided by 400 nanometers, and then minus 2 electron volts, and that gives me 1.1 electron volts. Which, if we're looking for the velocity, now we're going to set that equal to 1/2 mv squared. Now, that's where we have to be careful. We can't use 1.1. This is electron volts. So we have to multiply this by the charge of an electron to get it back to joules. So 1.1 times 1.6 to the negative 19th equals 1/2. And remember, the mass of an electron is 9.11 to the negative 31st. Times v squared, and that gives us a velocity, small velocity here, of 6.2 to the 5th meters per second. All right? Okay, hopefully that will give you guys enough information to move on into the next handout. Okay, good luck.